At about 6 o'clock in the morning on September 14th, 2015, scientists witnessed something no human had ever seen. Two black holes colliding. Both about 30 times as massive as our sun, they had been orbiting each other for millions of years. As they got closer together, they circled each other faster and faster. Finally, they collided and merged into a single, even bigger black hole. A fraction of a second before their crash, they sent a vibration across the universe at the speed of light. And on Earth, billions of years later, a detector called the Laser Interferometer Gravitational Wave Observatory, or LIGO for short, picked it up. The signal only lasted a fifth of a second and was the detector's first observation of gravitational waves. What are these ripples in space? The answer starts with gravity, the force that pulls any two objects together. That's the case for everything in the observable universe. You're pulling on the Earth, the Moon, the Sun, and every single star, and they're pulling on you. The more mass something has, the stronger its gravitational pull. The farther away the object, the lower its pull. If every mass has an effect on every other mass in the universe, no matter how small, then changes in gravity can tell us about what those objects are doing. Fluctuations in the gravity coming from the universe are called gravitational waves. Gravitational waves move out from what caused them like ripples on a pond, getting smaller as they travel farther from their center. But what are they ripples on? When Einstein devised his theory of relativity, he imagined gravity as a curve in a surface called space-time. A mass in space creates a depression in space-time, and a ball rolling across a depression will curve like it's being attracted to the other mass. The bigger the mass, the deeper the depression, and the stronger the gravity. When the mass making the depression moves, that sends out ripples in space-time. These are gravitational waves. What would a gravitational wave feel like? If our bodies were sensitive enough to detect them, we'd feel like we were being stretched sideways while being compressed vertically, and in the next instant, stretched up and down while being compressed horizontally. Sideways, then up and down. This back and forth would happen over and over as the gravitational wave passed right through you. But this happens on such a minute scale that we can't feel any of it. So we've built detectors that can feel it for us. That's what the LIGO detectors do. And they're not the only ones. There are gravitational wave detectors spread across the world. These L-shaped instruments have long arms whose exact length is measured with lasers. If the length changes, it could be because gravitational waves are stretching and compressing the arms. Once the detectors feel a gravitational wave, scientists can extract information about the wave's source. In a way, detectors like LIGO are big gravitational wave radios. Radio waves are traveling all around you, but you can't feel them or hear the music they carry. It takes the right kind of detector to extract the music. LIGO detects a gravitational wave signal, which scientists then study for data about the object that generated it. They can derive information like its mass and the shape of its orbit. We can also hear gravitational waves by playing their signals through speakers, just like the music a radio extracts from radio waves. So those two black holes colliding sounds like this. Scientists call this slide whistle-like noise a chirp, and it's the signature of any two objects orbiting into each other. The black hole collision was just one example of what gravitational waves can tell us. Other high-energy astronomical events will leave gravitational echoes too. The collapse of a star before it explodes in a supernova, or very dense neutron stars colliding. Every time we create a new tool to look at space, we discover something we didn't expect. Something that might revolutionize our understanding of the universe. LIGO's no different. In the short time it's been on, LIGO's already revealed surprises, like that black holes collide more often than we ever expected. It's impossible to say, but exciting to imagine, what revelations may now be propagating across space towards our tiny blue planet and its new way of perceiving the universe. If you enjoyed this lesson, we think you'll enjoy reading or listening to Astrophysics for People in a Hurry by Neil deGrasse Tyson. You can find a link to the book in the description below. And if you love our channel, please consider supporting our nonprofit mission on patreon.com/TEDEd. Thanks for watching.